Hello? There you go. I'll start now with the full expectation that we're going to have a load of people come in at the last minute. Yeah, there's another one, a load of people coming in. So one of the great pleasures of being honorary president of this illustrious society is you get to introduce fantastic people to give talks to all of us. So the prize today is called the Sir Frederick Bartlett Lectureship, and it's endowed by a trust in the name of the same man. It was first delivered in 1966. Now, I know a lot of people in Scotland won't remember 1966 for any particularly good reason. Is my joke at this point here. 1966, my brother was born. It's nice. My younger brother was born. And in 1966, something else happened that also didn't happen again, or hasn't happened again for many, many years. So I won't dwell on it. The Scottish people in the audience will be pleased with that. The prize itself recognises excellence in experimental psychology or an aligned discipline, excellence that has happened over many, many years, an extended period. And this year's Bartlett lecturer is Mike Burton, sitting over there. You will know him. I'm going to give you a little bit of background on Mike, not much, because I'd rather listen to him than speak. So he's been around a bit, to say the least. So I also have a pleasure of looking at people's CVs, which is always, anyway, humbling, to say the least. So Mike's been to many universities, had positions after his PhD in, I'll list them, Nottingham, first one, Stirling, Aberdeen, Glasgow and York, and in Glasgow and York he was head of school a number of times, twice, I believe, is that right? Twice in the first one, yeah. So he's, as I say, he's been around. As you all know, his main work has been in the area of cognitive science, broadly conceived, and he's a particular expert in, his particular expertise is in face recognition. And that work, as we will have seen, most of you will have seen this afternoon, has completely shaped the field, which is remarkable. And all the contributions that he's made, both methodologically, theoretically, and in terms of his applied work, where he's worked with the police, I think, in an academic sense, obviously, and also worked with passport agency, again, not having your passport checked, but helping other people to get it right. So remarkable career. He's supervised around 20 PhD students, which is a lot, as you can probably appreciate. I was just talking about this, we once examined together because there was a PhD project in Cardiff on face perception, and I was the other person in the room, so I was just the internal examiner, and we had to run from a pub clutching our sandwiches because they were so inefficient at bringing them to us in the pub, so it was quite an ordeal, wasn't it? Anyway, so Mike has also supported many ECRs in his time and colleagues over an extended period. So he's received many honours in the past, amongst which this must be your favourite. Must be your favourite. So I know you're all eagerly awaiting his presentation, so I will stop talking now, and I hope you'll join me in giving him a warm welcome to the stage.
Thank you, Rob, for that overly generous introduction. As he has mentioned, I've been around a while. I've been around EPS for quite a while, which means that I've been to a lot of these talks. So I am acutely aware of what a great honour this is. It really feels like it. So thank you to the Society, thank you to the committee for making the award. Thank you also to Rob Jenkins, who organised a fantastic symposium this afternoon. What a treat it was to listen to all those papers. So that was great. Thank you, Rob. Okay, Bartlett himself was quite critical of the prevailing methodology of his day. Here's a quote from his most famous book, Remembering: "While experimental psychology has to arrange external conditions with an eye to uniformity and control, the experimenter should never hesitate to break this external uniformity in the interests of stability of response." And that's a sentiment with which I wholeheartedly concur, as should become clear as we go through the talk. In its most practical form, simple form, it means that we used to use stimuli that looks like this, which give you a lot of control. You can do lots of stuff with it, but of course you lose their naturalness. These days we prefer to use stimuli like this, which have the opposite characteristics. And one of the things I'd like to try to convince you of in this talk is that that's not just an aesthetic preference, that you get some theoretical consequences of doing that. Okay. Let's go right back and strip it back to the basic problem. What is the problem of face recognition? And I'm only going to talk about recognizing people today in the sense of identifying them. I'm not going to talk about all the other things you can do with faces. Well, in order to recognize somebody, you have to be able to tell people apart. And actually, this is how we normally motivate the study of face recognition, for example, for new students. We say, look, faces are all the same, basically. They all have the same basic layout of features. So whatever the visual system is doing, it must be doing some remarkably sophisticated thing in order to pick up the subtle differences that do exist between people so that we can recognize them. But if you were to read the literature on face recognition, you could be forgiven for thinking that this is the whole problem, because this is typically the part of it that is studied. Well, a few years ago now, Rob Jenkins and I raised the possibility that an equally important part of the problem is what we call telling people together. The idea is if you encounter someone on multiple occasions, or maybe you see a lot of different photos of them, they appear different on each occasion, and sometimes they can appear very different from one another. And yet, you have no difficulty, if you know the person, in recognizing that that's the person. So how do you tell people together? We've argued that it's important to study that part of the problem as well, for a couple of reasons. Firstly, because unless we study it, half of our discipline is missing. That is just part of the problem. But also, we have held that if you overemphasize one part of the problem, just the telling apart, it can lead you down some theoretical blind alleys, about which more we can talk a little later. Okay, so what I'm going to talk about today is lots of different studies about telling people together. And it turns out this crops up in all kinds of places in face recognition. And I'm going to start with some work from about 25 years ago, studying unfamiliar face matching. Now, this is from work led by Vicky Bruce. And in constructing stimuli like this, she was borrowing the idea of lineups. And you all know about lineup studies. In lineup studies, people witness an event, and then they're shown a lineup of people, and they have to say, was somebody that you witnessed in the event in the lineup, and if so, who is it? And the other thing you know about that is that it's error-prone. People are really not very good at it, generally. And so there's a huge amount of research in that, partly because it's theoretically interesting, but partly because it's practically interesting. We want our witnesses to be accurate. And it turns out that in good faith, they can be wrong. Okay, but in designing this stimulus, Vicky said, let's forget the event memory. What if we present a stimulus with no events to remember at all? You just have to say, is the person at the top one of the 10? And if so, which one is he? Now, what we found was that people were surprisingly bad at this task too, even when there's no event to remember. And I want to emphasize the word surprisingly. So surprisingly that we didn't believe it at first. And then also surprisingly in that we went through a period where no one else believed us either. In fact, this isn't what we were studying. We were studying with Peter Hancock, who's here too, we were studying a comparison with automatic face recognition at the time. And we just wanted some human data against which to compare it. In those days, automatic face recognition was bad. And we assumed that the humans would be good at this, and they weren't. So why? What's going on? By the way, if you're sitting there thinking it's number 2 or number 5, you're sending the wrong guys to prison, because it's not. The person is not present, actually, in this display. Okay. Now, it turns out that unfamiliar face matching is hard. It just turns out that it's hard. And you don't need sort of contrived displays like this to show it. You can just get it right down to its simplest form. Here are 2 photos. Is it the same person? Yes or no? This has been shown quite a few times today. It was shown a few times in the symposium this afternoon, but none of the speakers said whether it was the same person or not. So I invite you to decide whether you think it is the same person or not, and also to decide how confident you are in that. What would you have riding on it? Okay, now I'll tell you the answer. The answer is that it is the same person. And these images were taken just seconds apart. They were taken with different cameras, and they have different settings, for example, different perspective settings by default. There's also a very slight pose change. The person's got a chin up a little bit higher in one of them than the other. And just those small differences are enough to make this quite hard. Even if you got it right, some people are very good at this. Most people, even if they get it right, they're not 100% sure. So why is it difficult? One of the interesting things about the problem is that actually people don't know it's difficult. And let me just illustrate this. If you were to describe this demo to somebody not in the room, you'd say, well, the lecturer showed us 2 pictures of the same person and we weren't really sure whether it was the same person. And whoever you're talking to will say, well, why? Was the quality poor? Were the images, taken a long time apart? Were they showing very different poses, very different expressions? No, none of those things. In other words, whoever you're talking to will try to explain the difficulty in terms of the stimuli. But there's nothing wrong with the stimuli. The stimuli are fine. The problem is you. If you don't know this person, this is a difficult task. By the way, in case you're wondering, one of the reasons it's difficult is not because I'm showing you them in grayscale. If you show it in color, you can now see the 2 cameras have got different color default characteristics too. It doesn't make it any easier. Okay. Unfamiliar face matching is hard. Have a go at this one. This is not the same thing, is it? Okay. These pictures were taken decades apart. The lighting is totally different. The expression is different. Okay. And yet what you're not doing is sitting there thinking, oh, are the corner of the eyes the same, or some sort of piece by piece. It's Barack Obama. Of course it's Barack Obama. These 2 things are very different. Now, it took us a while to persuade people that they were different, that unfamiliar face recognition, unfamiliar face matching was hard, and it's a consequence of the perceiver, not the stimulus. It's hard now to put ourselves back 25 years when we were first sort of going around the country trying to say to people, hey, unfamiliar face matching is hard. The reason it's hard to put yourself in that position is because this is now generally accepted in the scientific literature, not so much in the applied literature. Okay, not so much in the applied world, I should say, of policing and security. Here's the kind of objections we used to get when we first started talking about this. People said, okay, in your lab experiments, you're typically showing people 2 images, 2 photos, and that's a rather unusual situation to be in. The situation where unfamiliar face matching really matters is if you're doing photo ID, if you have to match me against my passport or my ID card or whatever it is. Okay, that's the real situation, and in that situation you've got movement, you've got 3D, you've got all this other stuff which presumably supports it. So, little lab experiments with pairs of photos just are not going to generalize anyway, so it doesn't even matter. That's one objection. The second objection, and this one we still get whenever we work with the police, is they say, look, your experiments are done on undergraduate students, which is true. They typically are. And the police say, this is nothing like the people we deal with, our highly motivated witnesses, our highly trained police officers. You're just not going to get generalization from your sorts of experiments to the real situation. Well, maybe. A more academic objection we used to get is, you've made this task look harder than it is by the selection of stimuli. So in particular, when you've been choosing foils, when you should say they're different people, you've gone out of your way to find people who look very like the other person in the face pair. Well, you know, one tries not to do that, of course, but maybe that's what's happening. Now, it turns out that none of these objections survive test. Unfamiliar face matching just is hard, even taking these into account. And I'm going to show you one experiment that just addresses these. There's a whole sequence of them, but I'll just show you one of them. And this is an experiment with the Australian Passport Authority. It's work done in collaboration with our colleagues at UNSW, Richard Kemp and David White. And I always pause and thank the Australian Passport Authority for two reasons. Firstly, they gave us access to their officers to test. Secondly, they allowed us to publish the research even when it wasn't flattering to them. And since we did this work, I've actually tested passport officers in several different countries, and you always get the same results. So I don't think what I'm going to show you is peculiar to Australians. What makes it different is they're willing to have the work published. Okay, here's what we did. We got each officer sat behind a desk. We got a volunteer student approaching them with photo ID, and the officer just has to say, yes, that's you on the ID, or no, it's not. That's the whole task, right? When it is the person, it's a photo of them we took 3 weeks earlier. Real passports in Australia, same as the UK, can be up to 10 years old, so that would be even more difficult. These are only taken 3 weeks prior to the experiment, and we had them checked for passport compliance. So in other words, these are exactly the kind of photos these people see every day as part of their working lives, okay? The volunteer students, when we were carrying the wrong ones, all we did was we mixed them up within the group. We had 32 volunteers, half men, half women. We never swapped across genders, so we just kind of tried to find pairs that we could swap within them. So we didn't really have the opportunity to go and look for somebody's brother or somebody's lookalike in order to do this. So I think you can't really accuse us of choosing the foils wrongly. And just in case you're thinking, well, maybe Australian students are quite a homogenous group, they're not. Here they are. Okay. So you haven't got a lot of opportunity to swap them. We just chose by eye the ones. There's David White, half cut off there in the corner, who actually ran this. How did the officers deal with this? How did they do? Absolutely terribly. Here you can see on the y-axis is their overall performance. I'll just show you percent accuracy in this slide. Some of them are getting 100% right. They're getting it all right. Some of them are getting down at 70. Chance is 50 in this. Most people, the sort of mean here is about 90. In other words, they're making 10% errors. And if you think, well, 10% errors isn't bad, this is a security critical decision that they make, and scale it up to the hundreds of thousands of people that pass through airports, more than that even. I hold that this is a very disappointing level of performance. This is what we always get. I've plotted this against how long they've been employed in the job. Some of these people have been doing the job for 20 years and they're getting 70% right. They've been on hundreds of training courses, they've got all the experience, and yet others, contemporaries who've been doing it 20 years, are getting 100% right. This is what we always get. There are big individual differences in this task. The mean is much lower than you'd like it to be for your security situation, and it turns out, although I'm not showing you here, that these individual differences are very stable. Okay. So unfamiliar face matching is difficult even for people who are paid to do it. Okay, so that's a practical example of why it matters. Can we begin to use that to understand human face recognition, which is what they're in the business of doing? Well, I'm going to show you some empirical studies and some modeling studies using that. I'll start with some empirical studies, and this, again, is work done with Rob Jenkins. We often use stimuli a bit like this for our studies. These are Dutch TV presenters, and if you don't know them, if you don't watch TV in Holland, your task is how many different people are there. And if you ask people in the UK who don't watch Dutch TV, they'll say 6 or 7 or 8 or something like that. You can probably see some of them are the same. If you ask people in Holland, they say 1, because it's all the same person. Now, even if you guessed that it was all the same person, you don't have a sudden aha experience.
response, right? You don't think, of course it's the same person. You think, oh, well, Mike's deliberately chosen some stimuli to look very different from one another from someone who can look different from one another. You don't naturally cohere these images into a single person. Try someone else that you might know. If you know this person, if you know the actor, John Travolta, you just have almost the opposite problem. Your system is telling you it's John Travolta, it's John Travolta, it's John Travolta. You almost have to look to see just how different the images are one from another. They're massively different one from another, just as variable as the ones on the last slide, and yet the experience is entirely a different one. I took a gamble here about the mean age of this audience. When I'm presenting this to students, I use a Harry Potter actor. But, you know, the point is the same. If you're unfamiliar with somebody, superficial differences between images can be taken for identity differences, that they're different people. Now, just to put some meat on this, I'll give you an example of doing some studies with this. In one study, we developed a card sort technique where the person on the right you've already seen, we mix up photos of her with somebody else. The person on the left, again, is a Dutch TV presenter. We just print them all off at passport size, shuffle them up on a table, and we ask participants, sort them into piles, one pile per identity. But we don't tell them how many piles to expect. And you see massive difference. So there are only two people. The UK viewers, for this particular example, sorted them into between 7 and 8 piles. Actually, the modal response was 9. So they think there's 7 or 8 or 9 different people here when there's only 2. You do it in Holland with exactly the same stimuli, they get it right. Their familiarity allows them to cohere together these superficially different images of the same person. And you might say, well, these people, this is a difficult task, right? Because the two people look quite similar to each other, which they do. But have a look at what happens when you look at the people who don't know them, the UK viewers in this case. How often do they make a pile with both people in it? That is, how often do they confuse them? Very rarely, less than once per participant for these stimuli. So the problem here isn't telling people apart. The problem here is telling people together. And we've argued that to understand familiarity, that's a very critical component that you have to understand, and it is little studied. Okay. I'm going to move on to some modelling studies to try to get hold of what is going on when we are cohering together multiple images of somebody we do know. So if we think about the people that we do know, we can do this magical thing. I've been mostly showing you images of people you don't know, but we can do it, as I've shown with a couple of examples, with people you do know. How do we try to model that? Well, in one analysis, what we try to do is we try to work out a statistical description of multiple images of a single person. And for these studies, we just use a very, very simple statistical technique. We use principal components analysis in order to draw out principal dimensions of variation in a set of stimuli. We usually use Hollywood actors just because you can get lots and lots of images of them, and it's just very easy to do. Okay. They're unconstrained in this sort of way, and all we do is run a principal components analysis on lots of different images of a single person, Hugh Jackman, in this case. Now, PCA, principal components analysis, has a long history in automatic face recognition, but its normal use is to analyze a single image of many, many different people in order to work out a space in which faces in general vary. So you might have a dimension that codes, long, thin faces to shorter, fatter faces, or you might have a dimension that codes darker faces to lighter faces, or those kinds of things. That's not what we're doing here. What we're doing here is just taking as many pictures of Hugh Jackman as we can and doing a principal components on just him. And then we ask, well, how does Hugh Jackman vary? And then we do the same thing on another actor, or another actor at a time, let's say Tom Cruise, and we can get a space of all the images of Tom Cruise that we can get hold of. What happens when you do that? What sorts of dimensions do you get? Well, I'll show you the first couple of dimensions from a PCA of Tom Cruise. What you're seeing in this first animation is an animation of the first component that comes out of a PCA of Tom Cruise images, animated from a low value on that first dimension to a high value, and all the other dimension coefficients are held constant. So it sort of shows you what is coded by that dimension. And what you see is it codes, firstly it codes rigid change. Faces change non-rigidly, as mine is doing as I'm talking to you, or you express. First component isn't interested in that, doesn't have any of that in it. It just codes viewpoint left to right. Second component just codes up and down. So these are just, again, rigid variants. These are just viewpoint dimensions, but they're the early ones. They're what you get first. And this is what you always get. This is from a Tom Cruise PCA. If you did it on another actor, you'd get the same dimensions out. This is what happens. If you go down a little bit and you start to look for some of the later dimensions of variation, then you start to get some idiosyncratic variation. So here's the sixth component of Hugh Jackman in Hugh Jackman space, and you see it sort of codes a smile. If you look at the sixth component of Tom Cruise, it has something in common. It's about the mouth, but it's coding a different set of variation from a kind of dime-turn mouth to a grimace where the corners of the mouth go backwards rather than up in a smile. So this is where you begin to see, firstly, non-rigid variants picked up, but secondly, idiosyncratic variants. These people are varying in different ways. Well, I guess it's too much to ask that they would correspondingly go down all the dimensions, that the 14th dimension might be the same, 17th dimension might be the same. That would be too strong a claim. So what we could ask is, do the total dimensions of Tom Cruise cover the same range of variance as the total range of variance of someone else, of Hugh Jackman? Okay? And the answer is no. Here's an example of that. We take a picture of Hugh Jackman on the left, and we project it into a set of dimensions derived from pictures of Hugh Jackman, not including this one. And what you find is that this reconstruction basically shows you that you can build a picture like this from building blocks built of Hugh Jackman. If you try to project it into a space derived by pictures of Matt Damon, so you try to build a Hugh Jackman picture, reconstruct it in building blocks derived from Matt Damon, you don't get such a good representation. First, you do code the pose, the lighting. These are the things that everybody's got, so you can reconstruct that. What you can't reconstruct is the likeness, the identity of the person. In fact, what you end up with is something that looks a bit like Matt Damon. You can't build Hugh Jackman from Matt Damon. Okay? People have idiosyncratic variability. My face is different from your face on any given picture, sure. But also, my face varies in ways that are different to the way that your face varies. And that has actually rather a lot of consequences. Firstly, it gives a natural explanation of why unfamiliar face matching is difficult. Here's an item from one of our tests. This is a test that we developed deliberately to be difficult. This is for looking for people who are particularly good at face recognition. So the true answer here is that these are the same person. Most people, unless they're particularly good at this, say it's a different person. And you can see why, because they don't look very like each other. And that's because you don't know this guy, so you don't know what range of things can be him. So all you've got to go on is whether the pictures look similar, and they don't. Here's another item from the same difficult test. People quite often get this one wrong, and they say it's the same person, even though it's not the same person. Again, they're basing their decisions on the sort of superficial image similarity. So this pair is similar picture-wise compared to the top pair. So it's sort of not surprising that people find this hard. Bear in mind, it's the early components that do this picture stuff. Pose, lighting, this sort of thing. And they're the components that everybody's got, right? But they're also the components that code most of the information. The PCA delivers its components in the order in which they account for variance in the set. So in other words, most of the information in these pairs is not about identity. It's about the common stuff. So it's hardly surprising that people use that common stuff in order to make their decisions and are error-prone in the task. Okay. If people have idiosyncratic variability, there are other consequences. One is that we have to develop a model of face learning that is essentially statistical, not essentialist. What I mean by that is, what we're doing when we learn someone is learning how that individual person varies. Now, many of our theories of face recognition are essentially essentialist, implicitly essentialist. Let me give you one example. Even if you're not a face researcher, you know about configurable processing. In this situation, it's the idea that we recognize the people we know because everyone we know has some characteristic spatial layout of their features, some set of distances between their features that is characteristic of that person. Okay? What we have argued is that that is just wrong. You're not, as you learn a face, getting a better and better estimate of the true platonic measure of the distance between Mike's mouth and Mike's nose. Right? What you're learning as you're exposed to me is a range of things that can be me. And the only way to get that exposure is to just hang around me. Okay? You can't get it from anyone else because other people have got different variability. Okay. There are some empirical consequences too. One consequence is that photo ID will be unreliable because photo ID is the situation where someone who doesn't know you is checking you, matching you to a photo. And we know that's hard. Now, I've already shown you passport officers not doing particularly well on that task. Around the world now, loads of people have done this with loads of other people whose professional lives involve matching faces. Notaries, bouncers, checkout staff selling a bottle of wine to people and checking their age and so forth. In the UK last year, for the first time ever, we had to prove our eligibility to vote in a general election using photo ID. Loads of us involved in faces were writing all kinds of letters to everyone we could think of that this would not help. It wouldn't help the security anyway. And we've just tested some polling clerks who actually did that job for that general election. Lo and behold, they're no better at doing it than a random group of students, that is to say, not very good. So it is unreliable, and that's what you'd expect. It also suggests, and this is kind of important, that generic training isn't going to help. How can I train you better to match faces when really what you've got to do is get exposure to the particular person you're trying to match? I can teach you one person. It's matching people in general. Now, this is big business, actually. It turns out that face matching is offered by some big organizations around the world. There's an organization called FISWIG, whose members include organisations like FBI, CIA, Australian Passport Authority, in the UK, the London Metropolitan Police, and the Border Agency. These are bodies that both accredit training courses, but they also send their people on these training courses. Okay? Some of the bodies that I've mentioned also offer training courses, so it's a kind of big business. Now, Alice Towler, who's now in University of Queensland, but when she was working with us in York, she managed to get access to some of these courses given by these illustrious organisations, and she managed to test 400 people going on these courses. And she tested them on a batch of matching tasks. I've just in my illustration shown one of them, but she used different matching tests, several different ones, before they went on the course and after they went on the course. And here's typical data. It just is for one of those tests in the set that she used. Pre-training and post-training. I'm not allowed to say which is course A and course B, but I may have mentioned their organisations. It's those kinds of organisations. You compare them against the control group who take the same pre and post tests, but they don't do a course in the middle. And what you find is the courses just aren't helping. But one thing really does change as a result of these courses. She had 400 people nearly doing this. 93% of them said they had improved as a result of doing the courses. Now, you know, at first that's sort of lightly amusing, but actually it really matters because these are the people who end up in court, in government, making decisions on the basis of identity. And the evidence that these are the experts that you should take notice to is that they've been on these courses. Okay. They don't work. Finally, another prediction of idiosyncratic variability is that the type of variability you're exposed to will predict the type of variability over which you can generalize. So the people here on this slide are all the same person. It's an Australian pop star. And Kay Ritchie and I showed people sets of images like the ones in the top row that are very variable. We call them a high variable set. They just got from the internet different instances of this guy. Or we showed them what we call the low variable set. These are just stills from the same interview. I have to say, in some areas of face recognition, these low bottom row would be considered outrageously variable, far too variable, because we can't control lots about them, right? But we call them our low variable set. And what we found was that people were better at generalizing to a subsequent test if they'd learned the images like the top row. So if you get a sample over the variability, you're going to get better with your tests. Okay, you might be wondering about movement. What I've talked about mostly today is looking at individual images. Does movement help because faces normally move? Well, it is true, yes, it does help at the learning phase. So there's quite a lot of evidence that if you're to learn a face, you're better learning it moving in a video than learning stills. Whether that is because you just get more data points, more variable input, or whether it's actually to do with the movement per se, the jury's still out on that. I favour the less fashionable hypothesis, which it's just variability. But some people are invested in thinking it's the movement, which it may well be. It's not resolved. There's kind of pretty much no evidence that in normal circumstances movement helps at recognition. If I'd shown you those Barack Obamas moving, you wouldn't have recognised them any faster. Right? You're basically at ceiling anyway. Okay. All right. If we're to offer a statistical account of face recognition and face learning, if we say it's all about the stats, we ought to say something about the stats of faces. What about our exposure to faces? What do we know? Well, we don't know much. We did, again, with Rob, we made an estimate of how many faces people actually know in the modern world. And we offered an estimate in a paper 6-7 years ago of about 5,000. This was based on some evidence from which we could generalize, and that 5,000 includes both people you know personally and people you know from the media. Of course, we can only ever get to within an order of magnitude here, and in fact, in the paper we say we think about 1,000 to 10,000 is about the range we should be looking at. But even that very broad suggestion is kind of a bit puzzling already, because that doesn't concur with our evolutionary history, in most of which we were living in groups of 40 to 100 people. So how come we've got this capacity? By the way, we didn't test capacity, Rob and I. We just test how many they do know. We didn't ask how many could they know. But if they do know about 5,000, and we grew up in these sorts of groups, why? It's like you've kind of been equipped by evolution with a system waiting for the internet to develop. It just doesn't make sense. Quite a common game these days is to ask what can we learn from DCNNs in face recognition, automatic face recognition, which, as you almost certainly know, has suddenly taken off. It is fantastic now. The automatic systems are absolutely fabulous now, much better than humans. But the statistics of them are so different from humans, I think probably there's rather little we can learn from them. Clearview AI is the one that is most used in police and security settings around the world. You have to be a government agency in order to buy it. On its most recent website, it says its most recent model is trained on 50 billion face images, right? It's just sampled across the whole web. That's not like humans. It's difficult to get a hold of what 50 billion is, really. Here's 10 faces a second. If we have to wait until we've seen 50 billion, we're going to have to watch this continually for 158 years. In other words, that's, I think, exactly how long Canada has been an independent federation. Right. So, look, it's just not like humans. So what can we learn by the comparison? Well, not much, maybe. Okay. The actual real exposure to humans, certainly evolutionarily and in infancy, is that we actually see rather few people a lot. So the last demo that I'm going to show you, the last piece of work I'll show you, is some work with Andy Young and Robin Kramer, where we asked, well, what are the characteristics of a model that just knows a few people? And for this model, we just taught it 20 different people, and we only used 20 images per face. So we train a model using our standard PCA approach, and we constrain the images such that half of them are men and half of them are women, half of them are white faces, half of them are black faces. And again, we use Hollywood actors just because it's just easy to get lots and lots of images of them. Okay. So what we did with this was we did our normal PCA on the 400 images, 20 people of 20 images each. Following that, once we'd got our dimensions of variation, we then used what's called a Fisher face approach, which comes from early automatic face recognition, where you, following your PCA analysis, you then cluster your stimuli such as that you're trying to bring together images of the same person and separate images of different people. So this requires some top-down intervention. You have to tell the model, try to cluster these ones together and separate from these. So now we're introducing some top-down element too. Okay, so we do that. Then we get completely brand new images that it's not seen before. We throw it into the space, we see where it lands, and we hope it lands amongst images of the same person. That's the idea. That'll count as a hit. All right, what happens when you do that? Well, firstly, you get very high accuracy in that situation. That's really nothing to boast about in the modern world. I mean, you'd expect that, that's fine. But we can ask, well, in such a small, impoverished system as this, what are the dimensions doing in order to do that? And something quite interesting comes out. So here are the training items, and we're just looking at their coefficients on the first dimension of variability from that analysis. And what you find is that it has separated all the images of men from all the images of women. Each dot is an image, each line is a person. And it has simply divided them up so that the men are at one end of the dimension and the women are at the other end of the dimension. These images are not labelled for sex, right? So it has just discovered sex without being told it's there. If you have to divide up a set of this many images, and it turns out that half of them are half men and half women, that's a pretty useful thing to be able to divide it up by, and it's found it itself. Here are the test images, so these are images of the same people that it hasn't previously seen. Again, they're well classified by sex. We never asked it to classify by sex. We asked it to learn these individuals. You can take 200 people, none of whom it's seen before. It can't recognise these people because there's no one for them to recognise. We can, though, project them into the space we've derived. And what we find is that on the first dimension of that space, it categorises them by sex. So on the first attempt, just learning 20 different people, we've got a sex classifier. When we weren't looking for it, it falls out of a system designed to compute identity. Okay, so it's an emergent property. Now, this was very striking to us. We didn't expect it to come out like this, as neatly as this anyway. And it turns out that sex decisions in faces are a bit strange. We had worked on it some time ago and given up on it. Here's why. We've known for a long time, 40 years, that when you ask people to actually explicitly make sex decisions to faces, they're really accurate and really fast. So you can do that in well under a second, including the button press. So we know that. So we kind of think, well, what's the cue they're using? There must be something pretty easily that they can just read off the face in order to deliver that fast, accurate response. And there are many, many sexual dimorphisms in faces. There are anatomical differences between men and women in the face, and there are lots of differences between men and women you can pick up. And I know this because 30 years ago, I spent a summer measuring hundreds of pictures of faces. And we had in those days a rudimentary digipad that we were very proud of, actually. You could go around and measure this thing. But in the end, it didn't work reliably, and quite a lot of this was supplemented with a ruler. So things have moved on a bit from that. We found lots and lots of different ways of distinguishing men and women on average. The problem was, all those dimensions that we found had big overlap. So none of them accounted for how you could make this fast decision. It wasn't that we found the magical affordance in order to make the decision. In fact, you had to have rather a complex combination of cues in order to make the decision anything like as accurately as humans could do looking at the same faces. And yet what we found here is a system which has just done it for free when not looking for it. And I think that that is a very nice property of telling faces together and telling faces apart. It's not just sex. This system also picks up other socially relevant factors. So I told you that half of the faces were black, half of them were white. In this analysis, that's the second dimension. That has the same characteristics as the one that I've shown you with sex. So you can distinguish between those images, including with new images, even just on the basis of this very few numbers of people. So this is a system that is, as it were, growing up, not seeing many faces, but just facing the problem of how do you both cohere together the different ways that this person can look and separate out these different people. If you do that with very few faces, it turns out you get a whole lot of other stuff for free. Now, of course, an environment where an infant might see half men, half women might be usual, might be unusual. An environment where women see half black faces, half white faces will be usual for some people, unusual for others. Okay. The point is that what these dimensions are doing is they're picking up the statistics of the environment they're growing up in. Okay. And they're not trying to solve that statistical problem. They're just using whatever they've got in order to make the key core decision. This is our claim anyway. To make the core decision, how can I tell all these people apart from each other and together in their multiple manifestations? That's the whole problem, and it seems to be a very powerful thing to be able to do. Okay, I'm coming to the end now then. Here's my conclusions. To study face recognition, I think you have to take variability seriously. I think probably most people would agree with this. But there is a tendency, and I've done it hundreds of times myself, to think that controlling stimuli, making your stimuli as homogeneous as you possibly can, so the only way in which they differ is by your manipulated independent variable, is a good thing. But actually, if you do that, I think you're throwing away a lot of the information that we actually use. So the danger is you're just going to get the wrong answer. So learn to love variability. It is the signal in this case. Okay. Secondly, and I feel almost embarrassed to say this because it's rather a trite thing to say, study the nature of the stimuli and the nature of the task, because it's surprisingly difficult as experimental psychologists to do that, actually. We have, and I absolutely include myself in this, we have a tendency to do the next experiment that follows up, manipulating just one more thing from the last experiment that we did or that somebody else did that we want to challenge or whatever it is, to just carry on in the sort of setups that we use in our labs. And we can lose sight of some really kind of fundamental things like variability is what's going on here. It's not our enemy. It turns out to be our friend. One further source of variability, which has just recently become a problem, and that is that we now all know different famous people. There was a time when everybody knew the same famous people. But mass media has just fractionated that. And so we find with our participants, if we're doing an experiment where we want to compare familiar people and we use famous people versus non-familiar people, typically we use famous people from a different country that they wouldn't know, then we can no longer rely on them knowing the familiar faces. People know different people. And if you take the statistical argument seriously, then you've got to accommodate that because it's all about sampling. People's samples, people's experience has to be different one from another. So how do we build that into our experimentation? And it's difficult to do, and it creates methodological issues. And in some work with Holger Wieser and other people who are doing this around the world too, we are in some situations now tailoring our stimuli specifically to our participants before we even run experiments. And that causes great methodological problems because, of course, people are seeing different things, and that sounds, knee-jerk, like not a good thing to do. But I think that this is where we get back to the Bartlettian idea that actually, we're trying to get the response the same, not the stimuli the same. So if you're going to do this, then I think that we're never going to come up with a kind of killer experiment. We're just going to have to use divergent methodology and converging methodology in order to make our findings. And we just have to live with that. There is no sort of single way to do with this. And so it's a plea for diversity. Now that is a very Bartlettian idea. So let me finish on a Bartlettian quote. He actually gave several retirement speeches. I may be doing the same. Here's one from one of his retirement speeches. There is very little hope for a psychologist who is not prepared to become an effective collaborator. And of course, who could disagree with that? I am so grateful for the many, many collaborators that I've had over the years. Far too many to mention, but I do just want to mention the collaborators, long-term collaborators that I've had, the people whose work has fed directly into the work that I've talked about today. So thank you so much to all these people. Thank you very much to my employers, to my funders, and of course, today, thank you so much to the EPS. Thank you.
You want to take some questions?
Yeah, if people have them.
Questions, anyone? Okay. Do you want to take that? I can't see any questions.
You don't have to ask questions. You don't have to ask questions.
You said something at one point reminded me of experiments on perceptual learning in animals, some of them, where you were talking about grouping things according to, binding things together. And there's a long history of research on something called acquired equivalence, where actually labelling does draw things together.
Yeah.
So I wondered whether you fed that into your system as well as an additional way of blending things, rather than only going on the statistical properties of the visual stimuli you're presenting the system with.
Yes, well, when we do the stuff using linear discriminant analysis, in the final one I was talking about, where it's, as it were, found sex, that relies on you telling it. And I think I do think that's important, because we as face researchers tend to think of the whole stimulus as just the sort of face and that's it. But, if you see a new picture of Barack Obama, it's sort of almost never out of context. It's going to, Barack Obama today said that such and such, here's a picture of him on the news. Oh, right, that's another one I can add to mine. So I think that aspect of being told which ones to go here together is a core part of this. And again, we're not very good at studying it, actually, because it's hard.
Yeah, for sure, yes.
Fabulous talk, Mike. Thanks so much. You've talked a lot about increasing the understanding of how hard this task is, but you haven't really talked about interventions to make it better. Now, one intervention I take from your talk is that you abandon the idea that people can do this, and you just use automated systems, like we have automatic passport control systems now, because they're so good at it, and just sort of say, well, stop trying to get people to do this, because they can't. Yeah. But I wondered if you've thought of any interventions that might be effective, and you didn't say what those training courses that work, what they comprise, and whether there's something you could incorporate in training courses that might make people better at it.
Okay. Firstly, I think in principle the training courses are never going to work. They comprise a lot of examples, and they're supervised. They also, a lot of them teach you the Latin names for muscles, which is lovely. There's no evidence that actually makes you better at it, but it's lovely. We actually have got an intervention which actually has worked, in fact. And that is so obvious, and that is select people who are good at this in the first place. Now, the UK Passport Authority and some work we've done with them now do this. And everyone would think, well, why didn't they do that in the first place? And I think it's because we all sort of have this baseline assumption most people can do it. The way that the passport officers were chosen in the UK was on different grounds: security grounds, reliability grounds, this sort of thing. We'll get the people that we want as our officers, then we'll train them, is the sort of model. And they are now convinced of the fact that they shouldn't be doing that. So what they do now is they do have a prior test of face recognition ability. You don't have to be up in the sort of top 5% super recognizer range, but you do have to be higher than the mean in order to get on their training program to do this. So that is an intervention where we can actually take a psychological finding and say, here, do this and it will help, and I think it has.
Is it possible to estimate a capacity limit of how many individuals we could, in principle, recognise, given the problems that people have for recognising faces anyway?
I don't know. Have you got an idea about how to do it?
You're the face recognition.
I only, even trying to work out how many they do know is massively contentious. And again, some people just don't believe that estimate because it seems an absurd thing to do. We have to do some tests and then generalize up and make various assumptions, which of course we make explicit, but you can buy them or not. I can't think of a way to estimate the capacity. It is, I think the best thing I can say is practically limitless. There seems to be, it doesn't seem to be the case that if you watch a new sitcom, you have to forget an old one, right? So for all intents and purposes, it seems to be limitless, which is weird given our evolutionary history.
So I was wondering, in the, I guess it's more, well, both the telling faces together and telling faces apart. I mean, facial processing and I guess recognition as well is like a holistic process at the face of it, pun not intended. But I was wondering, so there's essentially what you're saying is there are no benefits from any sort of cognitive strategies you could pull. So I was sort of trying to compare shapes of ears and stuff like that. Yeah. So is that the case?
Yeah, so there is actually, I was a little bit just disingenuous there, and I'd meant to say this. There is a group of people who are better at it than others, and this is a group called forensic examiners. It's a very small group who work in forensic settings. They are trained on doing part-by-part analyses, as it were. They don't just look at them and get a gut feeling. And in fact, if you compare these people against people who are just naturally good at it, they're doing something else. Some very nice work from the University of New South Wales showing that. But these people are better than standard people at it. There's very, very few of them, and they're still far from perfect. They're still a long way from where you'd want to be in security-critical situations. But if you do the sorts of tactic that you're describing, you can get a bit better at it. Because they are trained and they train people to do it. But it is far too technical a set of descriptions to operate practically. For example, someone dealing with a passport queue or a checkout queue, it's just not going to work there. But I should have said there are some people who do get better. They're just not perfect.
Thanks for this wonderful talk. I'm wondering whether there are certain features that might be easier to detect than others. So I get that we are bad at it on average when you see a group of people, but maybe certain people are easier to distinguish from others? Yeah. Is that the case?
Yes, it is the case. And the people who are easier to distinguish than others have a number of characteristics. You can remember them better if you do a memory test and that kind of thing. I think the answer to that is that again, this comes back to the idea this is a statistical process and not an essentialist process. There is a kind of a sort of a way of approaching face recognition that says, where is the information about identity? And people often say stuff about, it's in the eyes or something like this. Where is the information about expression? Well, maybe it's in the mouth or something like this. People haven't come up with very satisfactory versions of that, and I think answers to that, even though they've gone in with the program of finding out where that information is. And my own view is it's just because it's statistical. If you've got a big chin, that's what people remember. If you've got a big nose, that's what people remember. It could be anything. It's just it's just what you get exposed to, and we don't have this sort of top-down, we'll divide up the face in terms of the words. What even is a nose? You couldn't really convincingly draw where it starts and stops. So I think it is just we get away from that sort of question. It is undoubtedly true what you say, though. Some people definitely are more distinctive than others, and those people are easier to recognise, easier to remember. Yeah.
Thank you. This is really fascinating. I guess when you first meet someone that you've never met before, you don't have any information about their face statistics, and so you're having to learn that. And so my intuition would say that you would have to kind of relax your expectations of what they would look like, and maybe as you learn, your kind of confidence, or kind of what you expect of that person to look like, kind of hones in. Do you know whether there's any evidence of that, or kind of maybe what happens when that goes wrong?
It's interesting that. I mean, there are certainly real situations where people seem to have a pretty poor criterion. So, the change blindness stuff, right, where somebody's asking directions, somebody's asking directions of a stooge, somebody walks between them carrying something obscures them, and meanwhile they swap the person talking, and oftentimes the person doesn't notice. That's completely consistent with what you're saying. One of the early versions of this, actually, I should say that the fact that unfamiliar face matching is hard was in the literature before we started to look at it. It just wasn't really talked about much. So Richard Kemp has a good study back in, I think it's 96 or 97, where they were testing out new credit cards, charge cards for a supermarket. And they had people who worked on the tills just dummying this. So they got some volunteers to go in, apparently buy some stuff, apparently pay with a card, and the supermarket checkout person just said, yeah, that's you, or no, challenge the card. And the error that they made predominantly was to accept a false one. So they made all the possible errors, but that was the error that they predominantly made. So that would be kind of consistent. I mean, I guess the passport officer has the opposite problem, right? Because you really don't want to kind of miss somebody and just let them in. It's good enough for me, So I guess it depends on what your task is, but they certainly both are right.
Thank you. Thank you so much for your presentation. I was thinking about the point of using actors in your studies, because it's possible that they become actors because they have something particular in their faces. It's something that I'm thinking about.
Yeah, I think that's really true, actually. The sorts of photos you see of actors are not the kind of things that are the sorts of photos you see of non-actors, as it were. This is actually, the practical way we dealt with this was, instead of comparing, when we want to compare famous people with non-famous people, we kind of used to take pictures from magazines or hairstyle magazines or something like that, and we could never really completely convince ourselves that we were doing a proper comparison. So we got into the habit of using actors, I mean, not for the modelling, but when you're going to show them to humans, of using actors that they would know and then actors that they wouldn't, often in a different country, and trying to cross over so the same stimuli are famous or familiar for some participants and unfamiliar for others, and then you also run the study in the other country. So as we've had, for example, collaborations with Australia, we often use people who are known only in the UK, and so they're or only in Australia, and so they're known in one country and not the other, so we can balance that off. But you, in principle, and we have done this, you can certainly do all these sorts of modelling techniques with images of people that you know, if you like. We do it for each other as well. It's there. It's just not as convenient.
So just one more question, I think, and then we should. Is that okay?
Yeah, of course.
Thank you for this. It was a great talk. I'm kind of curious, so I make maybe an assumption. I wonder whether whether it would be harder for me to recognize people from different ethnicities. And if that is so, I wonder whether that part could be trained in like let's say I'm Caucasian and I have a harder time perhaps discriminating people from a different ethnicity. Would that part be trainable, that I basically become better, at least to some extent, discriminating between different people from a different ethnicity?
Yeah. Well, the data on that, I mean, there is data on that. So people, It does seem to be that after early childhood, people do get slightly locked into that. So people can move as adults to a different culture and stay there for decades and still not quite catch up with people who grew up in that. There seems to be some critical phase for that. But, you know, the other race effect is the way that what you said is often called. Although everybody knows about it, it's not that big. It's actually quite a small effect. And so if you compare it with the effect, for example, of matching unfamiliar faces with familiar faces, that effect is huge. And sort of people typically don't know that one, but they do know the other one. So yes, the answer to your question is there, but it's there. And it seems to be quite locked in.
Right, well, with that, can we all thank Mike again for a brilliant talk?